Hi, hello, good morning or good afternoon, good evening to everybody. I'm Ronald Siat. Welcome to this new CivilFEM webinar. This webinar will be about how to design buildings, well, according to an earthquake or seismic forces using CivilFEM 2018. Thank you for attending. As you know, earthquake seismic design is very important in certain areas, certain zones. We will explain which will be the main strategies for designing earthquake resistant buildings to ensure health, safety, and security of buildings, building occupants, and its and building assets. Of course, we will show you that CivilFEM is a powerful tool, powerful software based on the finite element method with accuracy, with enough accuracy to pre-design a structure before a collapse or even afterwards for forensic studies. We can as well, after the post collapse, try to find which was the cause of the failure, and of course always find a solution. Okay, we will perform a complete seismic analysis, including we will explain. We'll use this building as you can see. We will explain more details later. Uh, we'll start with a linear model spectral analysis, where we can take into account the typical codes and the standard loads applied for buildings. As in Eurocode or AC code, it has its typical globe combination of forces and loads, and we will check and design the reinforcement of these elements for slabs, um, beams, columns, and floors, the footing, the shear panels, okay, the shear walls, and later we will go beyond, because with CivilFEM you can always go beyond and include a nonlinear and dynamic analysis. We can add nonlinear transient analysis, applying displacement versus time table on the foundation. We'll see later, and include nonlinearities as material nonlinearities for the behavior of the concrete, multilinear or short-term loads, stress and strain diagram for these materials. And for steel as well, we can include a bilinear behavior for its stress and strain diagram to take into account yielding or a possible failure of these rebars. We will see later, and study the typical failure points, failure nodes or connections in these structures, which we will see later that some parts of the model will be very submitted to big forces. Some usually in the basement are and the shear panels and some beams. They must be redesigned, so we can always perform a more detailed analysis in some parts. So, and as well, today we will explain a little bit the new enhancements of, or the next service pack, which will be released very very soon, the Service Pack 1 for CivilFEM 2008. Yeah, it will take us about 1 hour. Okay, so thank you very much for your patience. Oh, the first thing is the model description. This well, it's better if I open. It's a 12-story, 12-floor reinforced concrete building. We used beam and shell elements. We have here the model. Okay, see, this is our geometry. We have created points, lines, and surfaces. Okay, we can create them using the graphical user interface, our own graphical user interface of CivilFEM, using any available tool, or we can as well import the geometry from another geometry software modeler. Okay, and as well we can use instead of a graphical user interface, we can use a Python programming language. Okay, you can use well, very common or very standard Python commands, and to well, automate auto have a fast and automate a lot of processes using Python, because here it's very easy to set parameters for the distance between columns in one axis and another, and play with the height of the floors, so we can have them here in very common vectors or arrays. And well, and always we can use as well parameters here in CivilFEM, defining any property, distance, material properties, anything can be defined here with units. Okay, and even vectors, points, and if you want to use units, we can define any type of types. Okay, once we have defined our geometry, we can define our materials. We have defined ACI materials. Here we can define according to any library. We can define the materials are always predefined. So once we have selected one, the mechanical properties are automatically defined. Always take into account that we work with units, but units in CivilFEM, that they don't need to be consistent. What does that mean? It means that we can mix anytime for any entity and property. We can mix. We can define at the beginning use a consistent units, or we can by default the international system using meters and newtons, imperial units for feet or inches, or even mix them. Here we have defined kilonewton for forces and length meters, but anytime you can here define any entity using any other unit. Okay, we can define our geometry in inches, and some material properties can be changed to any other unit, because internally the software will calculate it independently of the units. Well, of course they are consistent internally, and at the end, and we'll see later, results can be displayed in any units. So always you can see any property changing any units, and using all your desired units, and later you don't need to be worried that that mixing units will give you incorrect results. So after defining the materials, we can define the cross sections of, in this case, there are concrete cross sections, and in this case, these sections can be reinforced. Okay, we can set bending and axial reinforcement by number of bars. So by here we have by amount. We set different number of bars with different diameters. As I told you, we can always mix the and set any unit for shear and for torsion for beams. Okay, we have defined 3 different cross sections which will be assigned for different parts. Some for columns. These are for beams, and these are for columns. Okay. The same for shells, for the floors and slabs. We can reinforce in the next step, which will be after creating the geometry and model. As you can see, we follow this follows a very easy has an easy workflow, which is all groups are divided into tabs usually from left to right, but it can be always you can change between tabs going to one side or the another or another, and after performing our model, we can define our mesh options to go to convert our geometry model to our finite element model. In order to perform this process, we have to define what we call structural elements. Structural elements are a combination or a set or group of finite elements with the same behavior. In this case, we have defined beam and shells. In this case, for a finite element or for structures that will have one dimension much bigger than the other two, which are beams and columns, we will and take into account as well flexural bending behavior. Beam elements are the most suitable. Then, if we want to just take into account for linear elements axial forces, trusses will be the best solution. Shells, which one of the dimensions, which is the thickness, is very small with respect to the other 2 dimensions. The most general case is the solid, with only just 3 degrees of freedom, which is our displacements. Our cables, it's a nonlinear element where we only tension will be taken into account for typical cables of bridges or any other cable structures, for cable stayed bridges and others. Okay, once we have defined, here we have our different structural elements, we can proceed with the mesh. Once it is meshed, here we have our different finite elements. Okay, we have defined here the floors, which are highlighted in blue, our beams, all the horizontal members, and as well we have our columns, which are in red, and our foundation, and I forgot, yeah, and we have our shear panels, our shear walls. Okay, from this is our meshed building. So we proceed with the explanation. The next, after creating the model, is already explained. The loading. Which are the typical loads, which are dead loads, live loads, I just include two simple loadings, but of course we can add more besides dead loads, which include the structure and self weight, and the structure in operation, which are the live loads. We the most important one in this case, it's the spectrum. We have defined the horizontal and vertical spectra using the square root of the, the sum of the squares method for the modal combination, and take into account a 5% of damping. According to your Eurocode, well, or of many codes, later we'll see we extracted the 20 modes, but we can extract more depending on of the code specifications. As you know, we can extract at least a percentage of mode which show us a percentage of total mass, 80%, 90% of total mobilized mass. We will see later. Here is, I will show you here in the software. After the meshing, we have defined these loads. Here, self weight and the live loads. Okay, it's not. I can plot it here in the. Here you can see the arrows, and we can define a spectrum analysis here in loads. We can define a user response spectrum. Okay, with if we want to define a user response spectrum with our table of frequencies and accelerations for vertical and horizontal. In this case, we have used the one defined by the Eurocode number 8, and we have this chart. Here we have for different damping, different values of accelerations versus frequencies. Okay, and for the vertical, we have another values which are double. We set the different parameters of the response spectrum, and we include here the number of modes and the type of modal combination. Well, this case was the CQC, and the direct combination method for different directions. We can pre-stress as well our structure if we want to, and later we go back. Here we have our different mode shapes of our building. Here, once we have performed, because the 20 mode shapes will be combined, and later this spectrum, this pseudostatic force, will be included as a combination as a load case for the final combination. Okay. Here are the different data for each mode, frequency, period, all the participation factors for each degree of freedom, for displacements and rotations, and here are the total mass. So as I told you, this is the total mass is this one. So until we get we extracted 20, but we can extract as many modes as we need according to the total mobilized mass. Okay, until we get an 80 or 90% of in one direction, in X, Y, or Z. Okay, and we can, each result will be stored, and we can plot the results for each mode. Okay, we have 20 modes, so we can go one by one. We can animate, of course, the process, and we can see here the different modes animated. CivilFEM has a video generation, and in this case we used that tool to plot our. In this part, we can check if there's any problem of resonance of any vibration, if any modal shape has a particular frequency which can cause resonance problems. Okay. Then we go. Well, I just add that after loading, the next step will be the boundary conditions, which in this case it was very easy, just to restrain the bottom part, the columns and foundation, and we define there are different loads, which are live, as I told you, the live load, the spectrum, and dead load. One important load, which wasn't included here, is can be torsional moment for each floor. To perform that, to create a torsional slab, torsional moment for each slab, we can. I didn't mention that after the mesh, we can always change any property using model utils, creating springs, or in adding masses, or creating insertions. Insertion connections will define a kind of tie-ins of degrees of freedom, and a very useful tool is, or util is, the connection. In this connection, we can define a master node, and for example, if we want to define a torsional moment for the whole slab, we can define a master node where the torsional moment will be applied, and then select rest of nodes which will be connected to it. Okay, if we show it, we will see here the connection. If we see here, we can, as you can see, all the forces applied to this master node will be applied with an equivalent process to the rest of the nodes. Okay, that will be another interesting force to be included in our independent load cases. Okay. Well, we continue with our slides. After performing our model of our independent, after solving our independent load cases, which are these ones, we have, if we go to results, we have different results. The three different load cases, the live load, and the combination of the spectra to be combined with the two rest of them, and the different modal results, 20 modal shapes, which were defined for the spectrum case, and then we can combine them using any safety factor that are provided by the code. We go here, combinations, we can, if we already have defined a combinations, I can use it. Okay, and here are they. I have defined 3 combinations, load combinations, multiplying with these coefficients, 2 for the ultimate limit state and 1 for the serviceability limit state. For each one, we have, of course, have to take into account the safety factors or the properties of the material changing the accordingly the data for each load combination. Okay, so the process is to define our load groups or load cases, then perform our load combinations for each. We have defined here. Sorry. So we have defined three new results. Okay, once they are generated, we have them here: ULS1, ULS2, and serviceability limit state combination. If we open it, I can plot results, typical results for each. I can plot even the selection. So I can plot, for example, well, bending moments, for example, for that floor. Okay, here it is. We can and as well plot bending moment in beams elements. Here it is, or we can plot it. It's better to plot it in 2D. In this case, for beams, it will be better. Well, after creating the load combination and check results of each result, we can perform the reinforcement design. Okay, to perform we can perform the design for the slabs and for the beams. And then the process will be, after performing the design of reinforcement of each load combination, is to perform an envelope, so we can get the maximum values of the design reinforcement. Okay, so for shells we have different methods for the rebar design. Okay, once we perform the design, the software will give us the total, the strict reinforcement amount according to the material pivots, which was limited by the code. And for shells, for the floors, we will have the 2 directions and 2 faces: X, Y, and top and bottom face. For the shells, that's for the shells, and for beams, we follow the same procedure. We perform a code checking or design for each load combination, and then we perform an envelope to always get the maximum the rebar amount, which will cover all the loading scenario. Okay, the worst case scenario will be covered by the final reinforcement created by an envelope. How do we design our sections of beams and shells? Always taking into account the interaction diagrams. Okay, so we get the same. There's a criterion which give us if the section is okay or not okay. Okay, depending if we can check here. Oh well, this is one of the results that we're plotting before. Okay, but as I told you, we can perform in the next tab after results, check beams or design beams, and the same for shells. Okay, once we have our result, we can, for example, open the final one. This is one of the checking. We can, as I told you, we can select any unit. For example, we can plot some results. Here we have them. Okay, for reinforcement, but we can always change the units if we want to, regardless the units that we have that were selected from the beginning, and now we are square inches per foot. Here we have them. So we perform the code checking or design of reinforcement for each load combinations, and then we can, and of course, I can plot anytime for any load combinations. We can plot the interaction diagram of any beam. For example, one of the beams of the top. So we can see, as I told you before, a kind of safety factor. If the point of the bending and axial force diagram, interaction diagram, if the point is inside, this is the reinforced and unreinforced cross section of that beam. This section will be okay with the reinforcement that has been defined previously. If we need more, the software will give us which amount is needed to get that section okay. And the same for shells. Okay, we will yes. Here we go again. This for beams, and we can create. I'll show you in the software. Another utility is once we have created the design, we can create an envelope of maximum values, or even taking into account the concomitant values. Okay, once we have them, we go here and we can plot here we will see that the worst part will be in the shear panels here. Okay, here we can see the worst, and later we will see that they will need a detailed study. If we plot results without the walls, we will see, okay, that results are not so high. The worst one will be in the sub-foundation, but later we'll see that we will need to design or redesign the reinforcement for the shear walls. Okay, so this is the linear. The same, we can create envelopes for forces and moments. The next part that can be after going to the shear nonlinear part or the dynamic part, we can perform a special study of the foundation. Okay, the foundation can be prestressed. Okay, this is our foundation, and we have defined curved tendons. Here you can see them. In order to release some stresses, because we found that it will be better to pre-stress that foundation to avoid that possible failure of the basement. Okay. If we define this, we can always perform a code checking and take into account this processing for our final model. For these tendons, we can always, here we can see, we can check the pre-stressing, and losses, immediate, long-term, and total losses for each one. So we can always take them into account, and you can see them, and check results if we take into account the tendons or not. Here is a kind of a comparison of the amount needed if we of river amount. It's dramatically changed if we define or not define tendons. Okay. Well, the next part will be to define, going always beyond, define a displacement diagram. Displacement here. I'll open you the next part. A transient, in this case, it's a transient analysis. Okay, always when we define a new, if we close or define a new analysis, we can always choose which analysis that will be defined. But always we can change here from one analysis or another. So there's no problem in that. Okay, so now I will add, we can add displacement in Y direction or in X. Here we show you, we can import this, always this is a table of times, this time in seconds versus the displacement in meters. As I told you, we can always change the units. Here, this for us is a 40-second chart of displacements versus time that will be applied to the basement. Okay, you have a displacement for each 0.01 second. So we have 4,000 displacements. Then later in CivilFEM, we can decide the accuracy of results. If we want the step increment in 1 second, half a second, or the same, or with the same or the same accuracy, having 4,000 results for each 0.01 seconds, or okay, a centesimal accuracy. So this is the same model, but in this case we have defined displacement in Y. This is the worst case scenario, and we can define it in X direction as well. Once we have defined our displacement, we just solve it with any nonlinearity. We can define this is in X and this is in Y direction, and we can add a cracking, we can add yielding, we can add contacts, large deflections. this is a video of the result of displacements in X and Y. But of course, we can with the history plot, or we can plot. I didn't show you as well that we can plot in the. We can check another utility that can be, any result can be plotted using clipping planes. Okay. Yes, we can check with this history plot. We can check different positions or different results for example, I said displacement of in Y direction in here in the top, in the middle, and at the bottom nodes, 3 nodes. If I plot them, here I have the results versus time. In 40 seconds, the displacement of these nodes. Okay, the one on the top, which will move, as you can see, which more amplitude, with more, and it will have more displacement, which is the one at the top. The distance between this node and the one of the basement is 44 meters. Okay, so this is how it moves in the 40 seconds. Okay, due to the displacement that was shown before. Okay, and of course we can always plot any other result. Okay, let's plot another result here, but we can select forces, moments, shear force. Any result can be plotted versus time, kind of time history result. So this is and I didn't show you which are the nonlinearities that can be defined. In this case, we have defined a nonlinearity of the material. Okay, we can change the data of our stress and strain diagram, and for the steel as well, we can set a bilinear material, so we can see plasticity or yielding of, to take into account the failure and take into account large deflections. Okay, so the next part, as I told you, is to study in detail some parts of our structure. In this example, we will create single models to check well, the crack behavior of the shear walls with different configuration of the rebars and the concrete, if it has a hole, if it's voided or not. Okay, this is study detailed case of each of these shear panels that I showed you before here these shear panels that go from top to bottom. Okay, we will study different configurations with no reinforced rebars, with this X configuration, or even if we can optimize the shear section, the shear wall section, including a hole at its center. Okay, we consider two type of concrete for the AC 318. We can activate the crack here in the material, and we will study the different crack behavior for each configuration, with an X configuration with the hole and this rebar configuration. And we will to perform the mesh. In this case, we have created truss elements because it's a solid element, solid case. We will use the insertion tool. The insertion tool will define a tying between the host element, which will be the wall, and the inserted element. So we don't need, and later we will see, we don't need the mesh to be congruent. The mesh can be independent. This is our wall, and this is our reinforcement, or our rebar. Okay, and we will solve with the same forces that coming from the general or complete model. Here we have our loading. Here, or different loadings. Okay, coming from the original one, and we will check, for example, cracking strains. Here you can see that this configuration will give us these cracks. Okay, and depending on the different configuration of walls, we can check the strain, so we can decide which will be the optimum one. This is for, here we have another model with this configuration. These rebars are defined using the insertion tool. Now with the next we'll see the improvements of this version. The definition of insertion and contacts, it's much easier. I don't need to do it one by one. Well, I can select all of them. All these elements will be inserted into the concrete. So the effect, the mesh of the nodes of the trusses of the rebars will be tied to the mesh of the wall with this insertion tool. Okay, so the next, yes, I want to explain everything, but I don't want to jeopardize your patience, so I will move to the next study in detail, which will be the connection of beam and columns. Okay, in this case, we want to reproduce a push over in order to get our demand and capacity curves and retrofit, or even as well perform a cycling loading in order to, with a nonlinear loading and unloading of this cycling load, we will see that the formation will not remain the same, that it will not be released. We will increase the load for each cycle, and we will see that there will be always a remanent deformation. Okay, this study will be more advanced. Okay, this is our model. We have defined as well a solid model, and with the same utility, setting insertions between of the truss of the rebar made by truss elements into the host elements, which are the beam and column solid elements. Okay, they don't We don't need to change the, as we can see. We will use as well contacts to join the different entities. So the mesh can be dissimilar, not congruent, because later we can glue them with contacts. Okay, the elements will be inserted, and the next step is how to apply the lateral loads equivalent to the cycling loads. We will apply one load in following one direction, and in the next step will be following another direction. Okay, that we will perform many different load cases with different directions and loads, one for shear and one for axial to perform the shaking action of the force. Okay, with this cycling load, the joint will get that progressive damage. Okay, will be similar to the behavior of the structure and the seismic action. Okay, later with a history plotting, we can get our pushover typical curves. Okay, depending on the configuration, or capacity and demand curves. Okay, in this case, we can see where cracking in here we can show you the model. This is our model. This is the joint of connection of beam and you have them. Okay, and we have glued. If we show here, we define contacts between, as you can see here, the mesh is different, so we just define contacts between them to be tied. That's very easy to define a contact. Is just select one structural element and another and define the contact. The type can be glued, but also, of course, for some cases we can define touching, breaking, advanced contact if we want to take into account friction or separation or other advanced properties. Okay, these are our load cases. Okay, and here we have an animation inside. We can get, beside the cracking in concrete, we will get yielding in these rebars. Okay, and here we have an animation. Here we have our cycling loads, and for each cycle you will see that it will get more cracking. After the loading and unloading, the structure will get more deformation and more and the failure and collapse will come, and the same for steel. Okay, so this is this part about the seismic design is finished. I just want to show you the new improvements for the new service pack, which will be released very soon. The new improvements, in general, will be a more easy definition of multiple connections and springs, easily done by graphically. A very important new material model, Duncan Chang, hydraulic material model. We can set for the seepage analysis hydrostatic pressure load definition. For solution process, we can, before it can be done but manually or using Python, is to reduce cohesion and friction angle until getting the collapse following the shear strength reduction method analysis for slopes or any other geotechnical structure. The shear retention factor in crack data will depend on the cracking strain, so it can be changed. You don't need to be set a fixed one, a constant. And for post-processing, we can set a new user result by using Python. That's very useful if we want our own result following a formula, taking tension, a square value of the tension in some node plus the shear stress in another in the same node, and plus the square root of creating our own, maybe our own code verification as well. We can do it now by Python, taking into account all the results that are given by CivilFEM. You can create our own user results, and a new result manager window, which will be very easy to plot or to manage sub result files. Okay, you will see them in the next if you download the next service pack. Okay, well, this for example, this example was done was shown in a previous webinar, the strength reduction method to obtain the failure of this slope of these sliding areas by reducing the mole Coulomb parameters, which are cohesion and the friction angle. So we can get a safety factor of this slope. Just to add that we in CivilFEM, we always want to share our knowledge. We have two ways of showing this well, our expertise is by in a practical software way, using CivilFEM and another software. We have the International Online CEA Education Center. We can tailor your any course to your needs. Okay, you can visit our this website. And as well, if you want to have a theoretical background, we have a finite element method masters using the UNED, the Spanish Open University, and this will be for next 2019 our 25th course after our last successful 24 postgraduate courses, which almost 4,000 registered engineers. You can visit this website to get more information. And as well, as a very important new, we invite you to be part of our CivilFEM community. Okay, here you can share your thoughts, experience. It's a free resource where you can find work samples and find people with the same doubts. So tutorials, forums, FUK, chat. But you can ask there to the tutors or the people of Incasaibe, which have more knowledge about the software. But of course, between you can please, we invite you to join. You can visit the community in CivilFEM, but after this webinar, you will have a short survey. And you can select if you want to join our community or not. Of course, it's free. You can join whenever you want, and it will be very, 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 very interesting and useful. Okay. Well, always take into account that there's always a free trial version of CivilFEM available here. Thank you for your attention. You can email us in these email accounts. And visit all our social media. This is our website, our YouTube channel. Okay. You have a complete resource of videos. This is our community, and our International Center of Computer-Aided Engineering, with different courses. And of course, our community, you can check videos, the installation, forums. Okay, you have everything here. Okay, thank you very much. We will answer your questions. If you you can ask them here using this platform, this webinar platform, or you can write us to support at civilfem.com. Thank you very much. See you in next webinar. Bye.